Lesson 2.6, Graphs of Rational Functions. In Lesson 8.3, you talked about fractional expressions and rational expressions. Similar idea, just now we're referring to them as functions. Okay. First thing we're going to talk about is the definition for a rational function. Let f and g be polynomial functions where g of x cannot be equal to 0. Then the function given by r of x equals f of x divided by g of x is a rational function. Okay. So basically f and g are polynomials. They're creating a fraction. G of x is in the denominator. That is why there is that condition, g of x cannot be equal to 0, cannot divide by a fraction. So that's our basic definition for a rational function. First thing we're going to look at with rational functions, of course, is the domain. So suppose we have f of x is equal to 1 divided by x minus 2. Okay. In the numerator, we have a rational function, 1. Okay, that's a constant function, it's a polynomial. In the denominator, we have another polynomial, x minus 2. So those are creating a rational function. Remember, when we're talking about domain, two main things we need to be aware of. 1, square roots. 2, whatever makes the denominator 0. Okay, in this case, an x value of 2 makes the denominator 0. So for our domain, we could write all reals except x equal to 2. Okay, remember we could also use interval notation. We're going from negative infinity to 2, union 2 to infinity. And that accounts for all real numbers except 2. Now we want to use limits to describe what is happening at x equals 2, the value that is not in the domain of this rational function. So if we go to y equals, and I graph this function 1 divided by x minus 2, make sure to have parentheses around the x minus 2, the whole denominator. And we go to the graph. At an x value of 2, we can see there is a vertical asymptote. Okay, so we're going to use limits to describe what that vertical asymptote means. So the limit as x is approaching 2 is the value we're working with. Okay, and I'm going to put a little hyphen there. That means the limit as x approaches 2 from the left of f of x is equal to, and then we're also going to have the limit as x approaches 2, and I'm going to use a plus sign. The plus sign means from the right of f of x. So the first one, when it has a negative or a dashed line after the 2, that's referring to as we're coming from the left. The other one, where it's a plus sign, that refers to coming from the right. So if I bring the graph back up, as we're approaching that x value of 2 coming from the left and going towards the right, our y values are approaching negative infinity. And if we look at the graph, as we're coming from the right, going towards that x value of 2, our y values are approaching positive infinity. So those are the two limits that describe what is happening at that x value that is not included in the domain. That is indicating a vertical asymptote, which we'll talk about next. There are two basic types of asymptotes that we're going to talk about. There's actually a third one, which we'll talk about later. But the two we've talked about in the past, vertical and horizontal asymptotes. Okay, the first one, a vertical asymptote, we're going to use limits to describe how we can tell if there is a vertical asymptote or not. And we kind of just discussed that in the last problem. So if we take the limit as x approaches a just stands for some real number. So the limit as x approaches a, some real number from the left of f of x, equals positive or negative infinity, or the limit as x approaches a from the right of f of x equals plus or minus infinity. If either of these two things are true, that indicates we have a vertical asymptote, okay, at x equals a. Now we're going to use limits to discuss how we can determine if there is a horizontal asymptote. Okay, similar idea, except we're going to take the limit as x approaches infinity, okay, of f of x, and that is equal to b, or we're going to take the limit as x approaches negative infinity of f of x. Either of these two limits, the limit as x is going to positive infinity going to the right, or the limit as x is going to negative infinity going to the left, if our values, our y values, level out and they're approaching some constant value, that indicates a horizontal asymptote. Okay? Two basic types of asymptote. Vertical, notice the limit as x is approaching some real number, some x value. For horizontal asymptotes, the limits x is approaching positive or negative infinity. Okay? So two slightly different ways we're going to use limits to describe asymptotic behavior. The next thing we're going to discuss are properties for the graphs of a rational function. Okay? Four main things we're going to focus on. Okay? First criteria here, again, this table is in your book. Okay? Might be a little easier to understand or look at if you look at your book. But here are the four basic things we're going to look at. First one, the end behavior asymptote. Okay, we just talked about vertical and horizontal asymptotes. The third type of asymptote we're going to talk about is the end behavior. What's happening as we're going to the right, what's happening as we're going to the left. There's three main conditions. N is referring to the degree of the numerator. M is referring to the degree of the denominator. Okay, so that's what N and M are standing for. Degree of the numerator, degree of the denominator. So if the degree of the numerator is less than the degree of the denominator, the end behavior asymptote is the horizontal asymptote y equals 0. Second one, if the degree of the numerator equals the degree of the denominator, the end behavior asymptote is a horizontal asymptote y equals a sub n divided by b sub n. Okay? So that one's a little more confusing to try to understand. If we had y equals 2x cubed over 5x cubed, the degree of my numerator is equal to the degree of my denominator. Okay, so then we're looking at comparing the coefficients. So my end behavior asymptote in this case would be y equals 2/5. Okay, it's a horizontal line. We're just using the leading coefficients of our highest degree terms. So that is if the degrees of the numerator and denominator are equal. The third criteria is if the degree of the numerator is greater than the degree of the denominator, the end behavior asymptote is the quotient polynomial function. Okay, so basically we would use polynomial long division or synthetic division. We would divide those two polynomials. Our quotient, whatever we end up with, that would be our end behavior asymptote. That would tell us, depending on the type of function, what's happening as we go to the left, what's happening as we go to the right. Okay, so that's the first thing we're going to look at. What's happening with our end behavior of the graph. The second one, probably a little easier to understand, vertical asymptotes. Okay. They occur at the real zeros of the denominator, provided that the zeros are not also zeros of the numerator of equal or greater multiplicity. So basically we're going to look at our denominator, we're going to set that equal to 0, find out what values cannot be included in the domain. The second part that's talking about, remember in 8.3 when we factored these rational expressions, if we got some factor in common in the numerator and denominator, we simply canceled those out. Okay? That is a hole in the graph, so that would not be included in our vertical asymptote. Okay? It must be a 0 of the denominator that is also not a 0 of the numerator. The third thing are the x-intercepts. They occur at the real zeros of the numerator that are also not zeros of the denominator. So we take our numerator, set it equal to 0. As long as those x values are also not zeros of the denominator, then those are going to be our x-intercepts. Fourth thing is the y-intercept. This is probably the most basic one and easy one to understand. You're going to put 0 in for x. The value you get for y is your y-intercept, as long as it's defined. So that just basically means as long as 0 is included in the denominator, or 0, is included in the domain, the value we get will be our y-intercept. Okay, so I would write these all down in your notes, and now we're going to go through at least one example where we're trying to find all of these things for a rational function. So in this example, we're going to analyze the graph of a rational function, which basically means we're going to look for vertical and horizontal asymptotes. We're going to look for the intercepts of the graph. We're going to use limits to describe the behavior of the vertical asymptotes. So looking at all of those things we talked about in that last definition. To make this easier when working with these rational functions, it is always a good idea to see if it factors. Okay. We look at this, x minus 1 in the numerator, that is already simplified, but this denominator factors into x minus 3 times x plus 2. Okay, so this is why we spent so much time working on those factoring skills. Those are going to come in handy right now. So first thing we can look at, doesn't really matter where we start, let's look for the x-intercept of the graph. Okay, if we go back to our last definition, the x-intercept occurs, number 3, at the real zeros of the numerator, as long as those are also not zeros of the denominator. So if we look, the real zeros of the numerator, x equals 1, that is also not a 0 for anything in the denominator, so that is our only x-intercept. X equals 1. Okay? Now we can look for our y-intercept. Okay? The y-intercept, if we go back to our definition, that's the fourth thing on here. I'm going through the intercepts first. I know that's not in order. The intercepts I think are a little easier, so we're going to start with that first. Number 4, the y-intercept. This is the value of f of 0. So basically we're going to plug 0 in for x and find out what our function is equal to. So f of 0 is equal to 0 minus 1 over 0 minus 3 and 0 plus 2. So if we simplify that, the numerator is negative 1. The denominator, we have negative 3 times 2, which is negative 6, which is equal to 1/6. So our x-intercept is 1. Our y-intercept would be 1/6. So far we found both the x and the y-intercepts. The next thing we're going to find are the asymptotes. Okay, so first one we're going to look at is the vertical asymptotes. Okay, that occurs at the real zeros of the denominator, as long as those are also not zeros of the numerator. So if we look at our denominator, now that we have it in factored form, okay, we have x minus 3 and x plus 2. So our VA, our vertical asymptotes, are the lines x equals 3 and the line x equals negative 2. Remember, asymptotes are referring to lines, so it's important you have x equals those values. 3, negative 2, those are also not zeros of the numerator, so both of those would be our vertical asymptote. The last thing we need to look at is the horizontal asymptote. Okay, if we go back to our last part, the first thing on here, horizontal asymptotes, this is where we have to look at the degree of the numerator and the degree of the denominator. So let's look at our function. F of x is equal to x minus 1 over x squared minus x minus 6. The degree of our numerator is 1. The degree of our denominator is 2. So if we look at these three conditions, if the degree of the numerator is less than the degree of the denominator, if n is less than m, the end behavior asymptote is the horizontal asymptote y equals 0. So whenever the degree of the numerator is less than that of the denominator, our horizontal asymptote is going to be the line y equals 0. Okay, so we found the x-intercept, we found the y-intercept, we found the vertical asymptotes, and we also found the horizontal asymptote. The only other thing we need to do is use limits to describe what those vertical asymptotes mean. Okay, so we're going to have the limit as x approaches 3 from the left of f of x. We're also going to have the limit as x approaches 3 from the right of f of x. Then we also have to have the limit as x approaches negative 2 from the left, and the limit as x approaches negative 2 from the right. Okay, so 4 things we have to find because we have to find 2 limits for each of our vertical asymptotes. So easiest thing to do, let's look at the graph of this function. So if I type in x minus 1 divided by x squared minus x minus 6, and we look at the graph of this function. Fairly crazy looking graph. Okay, many things going on. First, let's focus at what's happening as x is approaching 3. So find where x is equal to 3. Our first limit is the limit as x approaches 3 from the left. As we're approaching that x value of 3 from the left, what's happening to our y values? Our y values are approaching negative infinity. Okay, now if we look at x equals 3, as our x values are approaching 3 from the right, what's happening to our y values? Our y values are approaching positive infinity. Okay, so that's the limits that describe our vertical asymptote at x equals 3. We use a similar idea. If we look at what's happening as x approaches negative 2, as x approaches negative 2 from the left, our y values are approaching negative infinity. And if we look as our x values approach negative 2 from the right, our y values are approaching positive infinity. Alright, so we found the x-intercept of our graph, we found the y-intercept, we found the vertical asymptotes, we found the horizontal asymptotes, and then we used limits to describe what's happening at those vertical asymptotes. Alright, in your instructions when you do the homework, it's going to tell you to draw a sketch of the graph. I'm not going to require you to do that. What you should do is graph it on your calculator and look at all of these things, what's happening, and try to understand and analyze the graph yourself. The next example we're going to look at is finding an end behavior asymptote. Okay, so suppose we have f of x equals x cubed minus 3x squared plus 3x plus 1 divided by x minus 1. So if we look, the degree of our numerator is 3, the degree of our denominator is 1. So if we look at our conditions from before, if the degree of our numerator is larger than the degree of our denominator, and this is the case we have in this one, the end behavior asymptote is the quotient polynomial function. So what that means we need to do is divide these two functions. So 2 different methods we've learned how to use. Okay? We can use polynomial long division. It's kind of a long process, but we can use that any time. Or if the denominator is a linear binomial, meaning x plus or minus some number, then we can use synthetic division. Since that is the case this time, I think it would be easiest to use synthetic division. Our k value, since it is x minus 1, our k value is 1. Our coefficients are 1, negative 3, 3, and 1. So going through using synthetic division, bring down the 1, multiply, negative 2, multiply 1 times negative 2, 3 minus 2 is 1, 1 times 1 is 1, we get a remainder of 2. Okay. Remember what this meant. We started with an x cubed, and we divided it by a linear binomial. So that means these numbers in the bottom represent the polynomial we have left. So we would have an x squared minus 2x plus 1 plus a remainder of 2 over x minus 1. The end behavior asymptote is the part that does not include that remainder. So what we're looking at is x squared minus 2x plus 1. So now we're going to look at the graph of our original function. Okay, so I have x cubed minus 3x squared plus 3x plus 1 divided by x minus 1. If we look at the graph of that function, okay, a couple parts going on there. It's kind of hard to see, but what I'm going to do next is graph that end behavior asymptote, x squared minus 2x plus 1, that polynomial we just found. Okay, so look closely at what the graph looks like. Now if I go back to y equals, and we're going to graph our end behavior polynomial function at the same time we graph our original. If you look at the graph, we have our original, and there comes our end behavior one. So what that means is, as we're going to the left and going to the right, the end behavior, what's happening with our y values of our original rational function, has the same end behavior as the graph of x squared minus 2x plus 1. So we're taking a complicated function and we're using a more simple one, a simple quadratic, to compare what's happening as we go to the left and happening as we go to the right. Okay, so this is the end of the examples for 2.6. Okay, you can go ahead and get started on the homework. After this, I am going to go through one more example of analyzing the graph of a rational function. So if that is still kind of confusing, you might want to keep watching, and I'll go through another example. If you think you have a good idea, you can go ahead and try to get started on the homework. So I'm going to go through one more example of analyzing the graph of a rational function, looking for the x-y intercepts, the horizontal and vertical asymptotes, using limits to describe those things as well. So if we have f of x equals 2x squared minus 2 divided by x squared minus 4, remember the first thing we want to do is see if we can factor each of these parts. So if I look at the numerator, we could take a 2 out of each of those, and we'd be left with x squared minus 1. In the denominator, you should recognize that that is a difference of 2 squares, so that factors into x plus 2, x minus 2. Okay. Not done yet, because if you look at the numerator, that is also a difference of squares. So we have 2, x minus 1, x plus 1, divided by x minus 2, x plus 2. Okay, so we got everything factored. Now we're going to try to identify all of those different parts. First thing, let's look at, or look for, the x-intercept. Remember, the x-intercepts occur at the real zeros of the numerator that are not zeros of the denominator. So if we look at that factored form, the real zeros of the numerator will be x equals 1 and negative 1. Neither of those are zeros of the denominator, so those are both our x-intercepts. Now if we look for the y-intercept, remember the y-intercept occurs where we find our f of 0 value. So we put 0 in for x, find out what that simplifies down to, And you can go through that calculations. You can plug 0 in for x and simplify. And if you do that, you should get y equals 1/2. So x-intercepts are 1 and -1. The y-intercepts are, or is, 1/2. Next thing we're going to look for is the horizontal asymptote. Okay. Remember, the horizontal asymptote, we're looking at the degree of the numerator and the degree of the denominator. The degree of the numerator is 2. The degree of the denominator is 2. So if we go back to this, if those degrees are the same, then the end behavior asymptote is the horizontal asymptote, y equals the ratio of the leading coefficients. So if we go back, those degrees are the same, so our horizontal asymptote is going to be y equals the ratio of the leading coefficients, which are 2 divided by 1, which is equal to 2. So y equals 2 is going to be the horizontal asymptote. So the last thing we're going to look at are the vertical asymptotes. Remember, the vertical asymptotes occur at the real zeros of the denominator. So if we look at our denominator, we have x minus 2, x plus 2. So our vertical asymptotes are x equals -2 and +2. Those are both of our vertical asymptotes. So we use limits to describe those. The limit as x approaches -2 from the left, and the limit as x approaches -2 from the right of f of x. We also have to find the limits as x approaches 2 from the left, and the limit as x approaches 2 from the right. Remember, there's 2 limits for each of the vertical asymptotes. Okay, so at this point, the easiest thing to do is to graph and look at what's happening to our y values as we're approaching these x values. So if I graph this function, this is what the graph looks like. So we're going to focus on that x value of -2. As we approach that x value of -2 from the left, our y values are approaching positive infinity. As our x values approach -2 from the right, our y values are approaching negative infinity. Okay, so those are our 2 limits for that. Now we're going to look at what's happening as x approaches 2. As x approaches 2 from the left, our y values are approaching negative infinity. And as our x values are approaching 2 from the right, our y values are approaching positive infinity. Alright, so we found our x-intercepts by finding the real zeros of the numerator. We found the y-intercept by plugging 0 in for x and simplifying. We found the horizontal asymptote by comparing the degree of the numerator and the denominator. One of those 3 conditions, determine which one to use, and we simplified. And then we found the vertical asymptotes by finding the real zeros of the denominator. And then we used a graph to determine how to write the limits for each of those vertical asymptotes.